Welcome, ladies and gentlemen, here to the forum of the 18th group exhibit, Hydrogen and Fuel Cells here on Hanover Fair 2012. I would like to invite you to take place here for the next interview on stage with Professor Dr. Andreas Friedrich, Head of Department Electrochemical Energy Technology, Deutsches Zentrum für Luft und Raumfahrt, Institut für Technische Thermodynamik, and we will talk about energy storage with hydrogen as necessary component of the German energy transformation. Please welcome with me Professor Friedrich.
Hello.
Nice to have you here
Hello,
on stage. Have a place. So whenever you have a question, please raise your hand and I'll come with the microphone right to you. And you can participate in this talk here, of course, whenever you want to. Professor Friedrich, our topic is energy storage with hydrogen as necessary component of the German energy transformation. Everybody is talking about the German energy transformation. The whole world is looking at us, and nobody really knows how to reduce CO2 at the same time when we switch off the atomic power plants. How can we handle that?
Yes, sure. We have a huge task for the German energy transformation, and essentially the goals of the energy government is to increase the renewable energy up to 80% in 2050, and this means that we have to think in a completely different way. And looking now at this goal of achieving this, it will be necessary to have a chemical storage medium. It will be an essential requisite. And my point is, even if we don't need it now, we still can cope with increasing renewable energies, which is about 20% right now. But it makes sense to invest already now into the research, into the development of hydrogen as a storage medium, because we will need it if we want to fulfill these goals.
Yeah, everybody knows the problem with renewables is the wind is not always blowing, the sun is not always shining, but we need energy 24/7, so all day round. We have peak times when there's enough wind blowing, and then we have too much energy and we can't just put it in the grid because it's gone then. If it's once in the grid, it's gone.
Right. And we need a huge amount of energy, so there are calculations between need of storage between 10 and 40 terawatts of power. And due to the high energy density of hydrogen, this is a good possibility to store this large amount of energy, which will not be possible with the other means like batteries or air-compressed storage devices. So we need all of them, but we need also the hydrogen.
So if we take hydrogen, we have to produce the hydrogen. Hydrogen is not available in nature except the sun. There's enough of hydrogen there, but it's far away. But here on Earth, there's no hydrogen. We have to produce it. We have to produce it via electrolysis. Is that easy?
Essentially, the process is easy, but of course, when you want to technically realize it, especially under the specific conditions of intermittent operation, meaning to cope with the large fluctuations of renewable energies, you need some effort also for the electrolysis technology. And we at DLR, we have actually had already large projects in the past where we demonstrated this coupling between solar power and photovoltaics and alkaline electrolysis, and we demonstrated that this technology, alkaline electrolysis, can cope with very dynamic fluctuating inputs of power by photovoltaics. And essentially that's why we are also so excited now, because we have done this a lot of work during many years, that now the time is coming, so this will be a solution, a widespread solution.
What you're talking of is high solar, and this is already 20 years ago. In the 80s, you did a lot of work in Saudi Arabia, especially, with photovoltaic panels, producing hydrogen directly from photovoltaic. So you have large experience in that.
We have large experience with that, and we know that by constructing, designing the electrolysis plant accordingly, and by introducing some electrodes, specific electrodes, which we developed at DLR, it's very, we can cope with intermittent fluctuations. We can have a very high efficiency, so we achieved efficiencies of over 80% for the electrolysis, and the electrolysis was also very durable. We tested for 40,000 hours.
And it went directly from the photovoltaic panel to the electrolyzer.
Yeah.
You didn't switch it from DC to AC?
Right, yeah.
Okay, just directly.
Just directly.
And that was not a problem really, was it?
No, it was not a problem. As I said, there was some development effort, but at the end we could demonstrate a very stable and durable operation.
And you said you did that with alkaline electrolyzers, and I have always heard that alkaline electrolyzers can't cope with these changes in power density.
No, that's not true. They can. However, normally the electrolyzers are produced for industrial applications where you need hydrogen as a chemical, for reduction of metals or for desulfuration of fuels, and for that actually you don't need these features which you can integrate, which make them adaptable to intermittent operation.
So if we speak about hydrogen as an energy storage for the future, for our renewable energy future, we have to talk about electrolyzers, because that's an important point there. There are two kinds of electrolyzers, so far as I know. There's the PEM electrolyzers and the alkaline electrolyzers. We just talked about alkaline electrolyzers, but you're also doing research in PEM electrolyzers.
Yes.
Why do you?
PEM electrolyzers are very interesting technology, because they are also they can cope with the fluctuations as alkaline can also, but they have a very high power density due to lower inner resistances of the cells, and therefore they improve even more on the efficiency side, and you can also operate them in a large dynamic range. And this makes them very attractive because you can also build much more compact. And we are developing also the polymer electrolyzer as a next generation large-scale electrolyzer technology.
They're also safer because they're running dry.
Yes. So the gases are more pure. So with the alkaline electrolysis, which has a liquid electrolyte, therefore there's also some crossing of the gases. You have to control very carefully the quality of the gases. This is not so necessary for the PEM technology.
So I only hear advantages of the PEM technology and electrolyzers. There must be some disadvantages, and as I guess it's like always in this business, it's cost, isn't it?
Sure. So the base materials of the polymer electrolyzer is much higher compared to the alkaline. With the alkaline materials, you have nickel, you have KOH, which is very inexpensive, a diaphragma, which is inexpensive. So the material bases are much more expensive for the polymer electrolyzer, but they can build much more compact. And therefore, the research topic is now to reduce the cost for the polymer electrolyzers and to achieve this high power density.
So PEM needs a catalyst which consists of platinum.
Platinum, and the iridium oxide,
And also in bipolar plates there's titanium in it.
Titanium, so that's expensive. So here also coatings are necessary so that you can introduce cheaper materials. Okay,
so I would say better go the cheaper way. What do you think? Well, how the race will end in the end? Alkaline or PEM?
That's not possible to tell right now, at least for me. That's actually that's the nice thing about research. You don't know the result.
Do it at DLR. Very good.
So you can approach both technologies and then see at the end which one is the most inexpensive one.
Professor Friedrich, but there's also a way to produce the hydrogen directly from the sun. As I said, on the sun there's enough hydrogen because there is so much energy up there. We can produce it even on Earth, direct hydrogen from the sun, and you do it in Spain, don't you?
Right, so these are the colleagues in Cologne and DLR that are developing thermal cycles for hydrogen production. So you're using concentrated solar radiation temperatures of about 1,000 degrees, and then they can produce hydrogen by chemical reactions.
So there's no electrolyzer in between. It's a chemical reaction. In the end, you have the pure hydrogen directly from solar thermal factories, you can really say, down in South Spain.
Yes, right.
Could that work also in Germany?
No, because here actually we have not enough direct radiation. So you need the direct radiation in Spain or other areas, southern areas, in order to make this process efficiently, in order to make the investment,
or maybe we just need some more research in that. So one day we can produce the hydrogen directly without electrolyzers. Yes. Maybe that's also a topic for a DLR. Who knows? Okay. So for Germany, it's probably electrolyzers important for hydrogen as an energy storage system. But if you have the hydrogen, you have to do something with it. First, you have to store it. So you have to compress it or even to liquefy it.
Yeah. Of course, that's necessary. Of course, if you liquefy it, you lose some efficiency in the process. So at
30%.
Yeah. So at the end, the efficiency is less. So from our point of view, actually, a very attractive way of storing hydrogen and distributing it is either salt caverns, where you can store a very large amount of hydrogen, or the introduction or into the gas distribution, natural gas distribution system.
Okay. These caverns already exist for natural gas?
Yes.
Some already for hydrogen, actually. In United Kingdom, you told me, there are 2 of these caverns already existing for hydrogen.
Yes. Actually, yes, the use of hydrogen is not very exotic in the chemical industry. So they're doing this for a long period of time. And there is 2 salt caverns in Britain which use hydrogen, and 2 large ones in Texas for the petrochemical industry, where they have a large-scale hydrogen storage and the distribution system by pipelines.
There was a discussion in Germany about CO2 storage also in caverns, and most people didn't like it, not even the politicians liked it, so they stopped this whole process. Yeah. Don't you expect also some protests against hydrogen storage in caverns?
Well, the developments in Stuttgart, for example, my hometown, show that you have to be very careful and you have to inform very careful the public in order to avoid such
That's what we
protests.
Do here,
yeah. And therefore, it's necessary to inform the general public. But I don't think that there's a fundamental issue with this, because we are now living with natural gas storage in large amounts in salt caverns, and there's not much problems, in my view, to change to hydrogen storage, since we have already had this after the war. We had the so-called Stadtgas, which is a coal-derived gas which has had a very large hydrogen content, and this was not such a big problem.
So it's possible to put the hydrogen directly into the gas grid?
Yes.
But they always say you can only do it up to 5% or something like that. Why do they say that?
Because these are the present regulations, and these regulations account for the users. So some users can't cope with higher hydrogen contents. For example, natural gas cars have a quite low limit of hydrogen which they can cope with. But here, of course, we can expect technology processes, and 5 volume% of hydrogen in our natural gas system would be sufficient to store.
It's already huge, isn't it?
Yeah, it's huge.
It's very much. So we can use it right now, put the hydrogen directly into the gas grid, but then in the end, if you take it out of the grid, you have natural gas. So the expensive hydrogen and the pure hydrogen is in the end spoiled.
Well, it can be used for applications where you use natural gas, heat applications, but of course there the return, the money you get is quite low. It's about 3 cents per kilowatt hour. So another thing I think is very attractive to again separate the hydrogen, for example, by an electrochemical device, and therefore you can use the distribution system and then recover pure hydrogen for the mobility, which is actually where you can make a lot of much more money if you use it as a fuel.
So by gas reforming, for instance, like we do in the micro CHPs at home, as a gas reforming to have in the end hydrogen for from natural gas for the fuel cell, which will heat and power our houses.
Yeah.
That is one example.
That is one example, but what I'm thinking of, if you have a large amount of hydrogen fed into the natural gas distribution system, say you have about on average 2% of hydrogen, and you can extract again this hydrogen by...
It doesn't mix with the natural gas?
It mixes, but if you have a chemical process...
Not chemically?
Yeah, not chemically.
I see, see. Okay.
And therefore you can then could use again the pure hydrogen.
So that would be a pure filter then in the end?
A pure filter, yeah.
So I can put the hydrogen in, like, let's say in the north of Germany, because there's a lot of wind power.
Yeah.
Put it into the gas grid, and it goes all over Germany, and in Munich you can take it off and filter it and filter the pure hydrogen out of it.
Right, and can use it as a pure hydrogen application.
That would be a very nice application indeed. Something new also for me, which is quite interesting, and I hope it will take place. But you here at DLR, you have brought with you, not here on this small booth here, but you have a large place over there. You can have a look at it. You brought with you the Antares, which is an airplane flying on hydrogen.
Flying on hydrogen with fuel cell power, so it's a fuel cell powered airplane, and we see this actually also as a symbol. We have demonstrated that hydrogen technology has advanced to the point that you even can fly with it, and we want to demonstrate the Antares also as a symbol of the energy transformation by using green hydrogen in it only.
So it is not your aim to have our jumbo jets all flown on hydrogen with fuel cells. That's not possible, is it?
Yes, you should never say it's not possible, because somebody may demonstrate a difference, but it would be very difficult. You can demonstrate hydrogen propulsion in aircrafts for small aircrafts, and for the larger ones you can replace the APU. So I'm pretty convinced, I'm very convinced that we will see hydrogen and fuel cells on board of an aircraft as an auxiliary power unit, and the propulsion for small aircraft.
So for taxi, which is moving the aircraft at the airport, you can use the APU, and also for starting the engines.
Right, yeah. So there are many applications that you can fulfill, and actually this is the attractive feature of fuel cells. You can use the electrical power, of course, which you need for starting the main engines. You can use the water which the fuel cell produces for cabin use. You can use the inerting gas, which is the oxygen depleted gas of the fuel cells, for avoiding inflammation, possible inflammation in the cargo or a kerosene tank. And you can use also for emission-free taxiing, so the movement, the slow movement in the airport region without the main engines.
Hydrogen is so wonderful, you can even burn it, and they even tried it in the air. There was a Tupolev flying on hydrogen, like 20 years ago, and Airbus in Germany had planned a cryoplane, which is also was thought about flying on hydrogen, high in the air, producing the water from the hydrogen, and then you can take a shower on a long-distance flight. What about this vision?
Yes, as I said, it's a nice vision, but it's very difficult to realize in a traditional aircraft design. So, because the volumetric storage density of hydrogen is rather low compared to the liquid fuels, it would be a very bulky aircraft, and this is why it's probably
it will take a very long. Hydrogen is light, isn't it?
Right.
Very good. Okay.
But it will take a quite long time.
Quite a long time will we have that. But we will see fuel cells in airplanes, and if you want to see a fuel cell in an airplane, just go over to the Antares down there. You can see the airplane itself standing there. It has flown. It can fly 6 hours in the air. If you would like to meet Professor Friedrich at the booth of DLR, it's just over there. I would like to thank you, Professor Friedrich, for this most interesting talk with you. Our time is unfortunately over already. Thank you very much for your attention, and have a good day, Professor Friedrich.
We have small drinks at our booth right now, so if you're thirsty and you want to continue the discussions, you are very much invited to come to our
let's have a little party at the booth of DLR. Thank you very much, Professor Friedrich.
Thank you.
It was a pleasure talking to you. I would like to tell you that right now there's a next talk here on stage with FuelCon from Magdeburg. Matthias Bode will talk about latest trends in fuel cells and battery testing, so please stay tuned. Thank you.